Hello, I'm Matsukawa, and I'm working at the University of Tokyo. I'd like to explain about Chapter 3, columns with low strength concrete and or high axial load. First of all, the Chapter 3 contains 3 sections. 3.1 is general. In 3.1, features of Bangladesh columns that were mentioned by Rafikul-san and Maeda sensei is written, including brick aggregate concrete, low strength concrete, high axial load, etc. And section 3.2 is calculation of shear strength QSU and flexural strength MU. This is the main body of chapter 3. And section 3.3 is example of application. This is just a calculation example. And today I will explain mainly about section 3.2, calculation of shear strength and flexural strength. Before going to detail, I will explain about the basic concept of column lateral strength evaluation. When lateral load is applied to the column, mainly two types of failure pattern will appear. First one is shear failure, like this. And the another is flexural failure. Shear failing column will have a diagonal shear crack in the center of column, and flexural failing column will have a horizontal crack and river yielding on the both edge of column. Both failure pattern have corresponding strengths. Shear failing column is determined by their capacity by shear strength QSU. Flexural failing column, their strength will be determined by flexural strength QMU. Both lateral strengths, QSU and QMU, these are the very key factor for seismic aberration of columns. This is a backbone curve of example column. Sorry, just a moment. If shear strength QSU is larger than flexural strength QMU, the backbone curve will be like this. I mean, very ductile because of yielding of tensile river. But if shear strength QSU is smaller than QMU, shear failure, which is a very brittle failure, will occur. In that case, how to say, less ductility is provided in seismic evaluation. Shear failure is very dangerous. These are the pictures that were taken in a Kumamoto earthquake. There are some buildings collapsed due to shear failure. The shear failure possibly leads building collapse because of very small drift capacity. To avoid this type of collapse, it is very important to certainly find columns prone to brittle shear failure by seismic evaluation, and to increase shear strength by seismic retrofit. Today is a seminar for seismic evaluation, so I will explain about this part. To certainly find columns prone to shear failure, equations of both shear strength QSU and flexural strength QMU target different points in the strength distribution. Equations for shear strength QSU targeting a lower bound of strength distribution, and flexural strength QMU targets mean of actual strength distribution. And after the calculation of QSU and QMU, we calculate the ratio of QSU and QMU. If the ratio is larger than 1.0, the column is classified as a flexural column. Flexural column is basically allowed to have high ductility. If the ratio is smaller than 1.0, the column is classified as shear column. Shear column is not allowed to have high ductility, so we should provide low ductility for shear columns. This is a basic concept of strength evaluation. Let me go into concrete equations. First one is equation of shear strength QSU. This equation is current Japanese seismic evaluation standard equation, and this is our proposal, our proposing equation. As you can see here, the modification is very minor. The original Japanese equation is, how to say, is an empirical equation to adapt concrete strength larger than 13.5 megapascal. In this project, a reduction factor alpha L, which is a function of concrete compressive strength FC, is employed instead of a factor 0.58 to adapt for concrete strength smaller than 13.5 MPa. This modification has been examined by test result of both brick and stone aggregate concrete columns, like this. This is a current Japanese standard, and this is our proposal. Horizontal axis is concrete compressive strength, and vertical axis is tested shear strength divided by calculated shear strength. As you can see here, in low strength concrete zone, when we use Japanese standard, some overestimation is observed. But when we use a modified equation like this, the trend is very improved like this. And target of shear strength estimation is to estimate lower bound. As you can see, this distribution, lower bound of tested shear strengths are estimated very well, regardless of concrete strength. This is the reason that we employ these equations in this project. Next is flexural strength, MU. Before going to concrete equations, we have examined current Japanese equation using low strength concrete test data. This is a figure. Horizontal axis is axial load ratio, and vertical axis is tested strength divided by calculated strength. You may find two issues. In high axial load specimens, many specimens are going top, going higher place. And another issue is plain bars specimens are plain bars specimen tend to show smaller strengths. These are the issues to be resolved. So we have modified to solve these issues. For the columns with high axial load, an enhancement factor EH is employed to make axial load moment relationship close to general. This is a original Japanese relationship. And after employing factor EH, the curve became like this. And for the column made with plain bars and concrete below 13.5 MPa, reduction factor EP is employed because plane section remains plane assumption is not applicable for this kind of columns. So yes, after this factor, after we employ these factors, in the beginning trend was like this, but after multiplying factor EH and EP, trend is very uniform. And again, calculation of flexural strength target mean of actual strength. Yes, this is how to say 1.0. So mean of tested QMU is estimated very well. So this is the reason why we employ these equations. Remarks are written here. I don't repeat about the strength evaluation. But here is, as I write here, in addition to estimate drift capacity of columns, equations written in the Japanese standard or BSPP guideline seems to be applicable as shown in commentary C 3.3 in the document. So we have not modified such ductility evaluation equations. Only the, how to say, strength evaluation was changed. This is all from me. Thank you for your attention.